So today let's go over AP Physics C, Mechanics 2021, FRQ Set 1. So the first question tells us that 0.5 kilogram fan cart is placed on the level horizontal track of negligible friction, so which means there's no friction. And we turn on the fan, so it's moved from the left to the right, toward the right. And it goes down the incline, and there are two detectors, motion detector 1, motion detector 2. The question tells us that detector 1 measures acceleration of the cart from time 0 to time 3 seconds. And at t equals 3 seconds, it moves through transition to the incline, and motion detector 2 start working, measure the acceleration start from here to here, from the incline to the end. So, all right, so this is the graph, this graph for detector 1 and this graph for detector 2. So, as we know, we have 1, 2, 3, 4, 5 box from 0 to 2, which means each box is 2 divided by 5 is 0.4, so each box is 0.4. So this line should be 2 box, which is 0.8. And this line here is 1 box down, so it's negative 2.4. All right, let's take a look at the question. So the first question says, on the dot below, please draw basically it's just asked us to draw the free body diagram for the cart. The first one is on the horizontal plane, and the second one is on the incline. So on the horizontal track, we firstly need to draw mg, gravity, and also the normal force, which is equal to mg, but the direction is opposite. And surge force on the right side, toward the right, is produced by the fan. We call it F fan. On the incline, mg, we still have mg pointing downward. But normal force should be normal to the incline, so it's pointing upright. It should be less than mg. And we also have F fan. Okay. So the question tells us that if I turn on this releasing, so the fan exerts the same magnitude of the force on the car during the entire motion. So the F fan during the entire motion doesn't change, it's a constant. So part B asks us to calculate the net force exerted on the fan cart when it is on the horizontal track. So from the graph, we know on the horizontal track, the motion 1, detector 1 has detected the A1 has to be 0.8 meter per second squared. So we know Fn, because on the horizontal track, the only force that's caused the car to move is Fn, so Fn is just equal to ma1, which means it's equal to 0.50 kilograms times 0.8 meters per second squared, which is equal to 0.40 Newton. And part C, we need to calculate the angle of the incline. So the car starts moving from here on a horizontal track and then goes to the incline. On the incline, the motion detector has measured the acceleration of the cart is to be negative 2.4, same as 2.4 because it's negative just because the cart is moving toward the detector 2. So the magnitude is 2.4. And the cart is moving toward the right. So let's define the right to be positive. So the force Fn is toward the right. So 0.4, it should be Newton, but I will not write the units. So just 0.4 plus the total force. And we also have the gravity, right? Gravity is mg pointing downward. We need to know the component on the incline. So it's mg, which is 0.5 g times sine theta. That should equal to 0.5 the mass times the total acceleration, which is just a2. And from here we know a2 is 2.4. Okay. Remember the unit is Newton. Okay. So we know 0.5 g sine theta is equal to 2.4 times 0.5 is 1.2. Okay, which means sine theta is equal to 1.2 divided by 0.5 g. So theta is equal to inverse sine of 1.2 divided by 0.5 g. And we plug in into the calculator. So make sure you calculate degree mode. If it's in radian mode, it doesn't work. Okay, it gives you the angle in radians, not in degrees. Inverse sine 1.2 divided by 0.5 times 9.8, which is equal to 14. Looks like not that right. Let's check because 14 is too large. 0.5. Okay, so this should be like, forgot to minus 0.4 here. We need to minus 0.4. So we need to minus 0.4. So this should be 0.8. So it's just sine theta. Okay. So I think if that should be right if we change it to 0.8. Yeah, so theta should be 0.8 by 0.5 g, which is about 9.4 degrees. So part D. Okay, for part D, suppose careful measurement determines the angle of the incline to be 3 degrees larger than calculated in part C. Consider the following explanation. The scale used to measure the mass of the fan. Blah, blah, blah. Okay, basically it just says that the scale has some problems, so the mass is inaccurate, which makes the angle calculated inaccurate. So does this explanation sufficiently account for the observed discrepancy? Well, let's try to prove for that. From this equation, the Fn is a1 plus mg sine theta, which is equal to ma2. And from this equation, you immediately know that the mass doesn't matter because all mass cancels, right? We don't need to care about mass, which means this explanation does not sufficiently account for the observed discrepancy. There's no. Okay. Okay, so let's go to finish part B. Let's go to part E. Part A told us that experiments repeated for several trials, each with different angle on incline, and the acceleration of cars down the incline is measured for each angle. The graph below shows the plot of the acceleration A of cars as a function of the sine of the angle sine theta. So the acceleration of the down the incline, which is a2, from the equation we derived from in part D, we know a2, which is a here, is equal to a1 plus g times sine theta. So which means if sine theta is x, then g is my slope, or m. This is not mass, this represents slope. My a1 represents b. This is y. This is y equal to b plus mx. We know the slope should be g. So it's also to draw the best line for the data. You need a ruler to draw, but I don't have a ruler now, so we can kind of draw that's fine. I'm gonna use a pencil to draw that. So you can draw something like this. All right. So it's kind of a line of method. So let's pick 2 points, okay? Because the part E2 you asked us to use the straight line to calculate experimental value for acceleration due to gravity g. And you can pick 2 points, 2 points which are really far away. So the first point I'm gonna pick should be like, so each one is, this is 0.02, this is 0.04, 0.06, 0.08. So we're gonna pick this point. 0.08. So speed should be 0.08. Vertical axis 1.2, 1.3, 1.4, 1.4, 1.2, 1.4, 1.6, 1.8, so 1.6. Another point we can pick is from a point really far away from here, so we can pick this point, which is really nice. This point should be 0.42 and 5. Okay, so let's calculate the experimental value for acceleration due to g. The g is just simply the slope. So changing y over changing x, 5 minus 1.6 divided by 0.42 minus 0.08 should be meters per second squared, which is equal to divided by 0.42 minus 0.08, which is equal to 10 meters per second squared. Well, that's pretty close actually, right? A pretty good approximation. So point F, if the card were replaced with a second card of mass 1 kilogram that has a fan that exerts the same magnitude of force as the original fan, explain how the graph given in part E would change. Well, F fan is equal to MA1. It only affects A1, right? If M increases, A1 decreases. And if we take a look at this equation here, A is just B. So if A decreases, right? If A decreases, that means the entire, because A is B, so the entire graph would moving downward. So I would say that the graph would move downward because A1 decreases. Okay. All right, I think that's it for part 1. Question 1. For question 2, we also have a block of mass on the incline. The original height is h, and there's a loop with a radius r, and we also have a spring right here at the end. The block of mass is released from A and travel with a negligible friction. So lucky, we don't need to consider friction at all in question 2. So through the loop onto a horizontal surface, the contact with the spring and case mg to r with horizontal. Okay, point C is the highest point on the loop. Point B is the rightmost point on the loop. Okay, we need to express all algebraic answers in terms of m, h, r, and physical constant as appropriate. Oh, okay, so part A, dot below, draw the represent the direction at point B. Basically, asks us to draw the free body diagram at point B. So, wait a second, it's not free body diagram, draw an arrow, it's just an arrow, direction of the acceleration. So, we just need to show the direction of acceleration by one arrow. Okay, so when block moves to point B, it should have has a normal force, right? Pointing like to the left. and also should have gravity pointing downward, which means the total acceleration should pointing down left. So justify your answer because we have a normal force is pointing to the left and the gravity is pointing downward. That means the net force and net acceleration is pointing down left. Alright, so part B, derive expression for speed v of a block at point B. So in this case, right, we can use a law of conservation of energy. Initially, the energy for the block is mgh. It's initially. Finally, the block is moving, so it's 1/2 mv squared, but we also have some potential energy. The potential energy in this case is the height of B is just the radius of the loop, which is r, so it's mgr. So can all be cancelled, so it's gh equal to 1/2 mv squared plus gr, which means g is time, which is gh minus r equal to 1/2 mv squared. So that means we can, okay, so m should be cancelled. G 2g times h minus r equal to v squared, so v is equal to square root of 2g h minus r. So that's the speed of block at point B. Okay, part 2 for part B is derive the expression for the magnitude of the net force F at block at point B. So we have known the speed at this point is square root of 2g times h minus r. So we know the normal force Fn is equal to mv squared is 2g h minus r divided by what? Divided by the radius, which is r. We also know that so that another force is gravity is pointing downward, so which is just mg. This is equal. Okay, so the total force F is equal to square root of m squared. Write 2 in the front. First is 4 m squared g squared h minus r squared divided by r squared plus mg squared, which is equal to m squared g squared, so it's mg square root of 4 h minus r squared divided by r squared plus 1. Okay, so basically you calculate the value of Fn, then you can plug in into this equation based on Pythagorean theorem. You calculate the total net force. All right, so that's part 4. For question 2 is part C. Part C, in terms of R, derive the expression for minimum height h minimum necessary for the block to maintain the contact with track through point C. So in this case, what we want here is that we want make sure that the mg is equal to what is equal to my normal force, which is mv squared over r. So v squared in this case it's simply 2g times h min minus 2r, right? Because if you take on point C, the height for point C is just 2r. So it's minus 2r, not minus r. Which means G is equal to 2G of h minimum minus 2r divided by what? Divided by my r here. So we can also cancel G on both sides as 1 equal to 2 h min minus 2r divided by r, or r equal to 2 h min minus, so 4r, so 2h minimum is equal to 5r, so my h minimum is equal to 5 over 2 times r. Part D. It is determined that h is equal to 0.3 meters and r is equal to 0.1 meters. If the block is released from the height greater than that found in part C, what would be the maximum compression H max of the spring? So the total initial energy is my initial potential energy, which is mgh, and that should equal to 1/2 kx squared, which means mgh is equal to 2 mgh is equal to my k. What is the k again? K in this case is equal to, okay, let's see, k is mg over 2r, so just mg over 2r times x squared. mg and mg are cancelled, with times 2 on both sides, so 2r on both sides is 4rh equal to x squared, x max squared. So my x max is simply equal to 2 times square root of rh. Alright, so part E, a graph of a maximum compression of a spring as a function of height is shown below. The height h minimum is the height calculated in part C. Explain why section 1 appears as a horizontal line segment on horizontal axis. Because when h is less than h minimum, the block can't pass the loop. So the spring can't be compressed. Right, nothing is compressed, so definitely the x should be 0, right? Because it's not being compressed. Explain the reason for the shape of section 2 on the graph. Well, that's pretty easy, because from here we know x is equal to 2 times square root of r, also times square root of h, which means x is kind of proportional to the square root of h. And so that's why it's created a shape like that, downwards, like kind of like concave down, like that. And x at h min and x at h min is not 0. Right? Because we already have some energy, so this part is not there. And h min is not 0, right? So this is definitely not 0. Okay, the last part. We're almost done. Part 3, question 3. Okay, so now we need to use calculus to do question 3. A triangular rod with Lm and a mass big M has non-uniform mass, linear mass density, which is lambda equal to this is gamma x squared, and gamma is 3m over L cube, and x is distance from point P on the left end of the rod. So using integral calculus show that the rotational inertia I of the rod about an axis perpendicular to the page and through the point P is 3/3/5 times ml squared. Which means if you don't know how to do part A, you still know the answer, so you can still use that to do other parts. All right, so we know the rotational inertia I is equal to r squared dm, right? I found it on the formula sheet. And in this case, r is represented by x, right? Because we need to know the axis. The axis is 0 point P. So start from point P to somewhere here. Simply the x position of a point here. And this small mass, we call that dm. Okay? And the short distance is dx. So we can make r squared x squared, and dm is simply my linear mass density times dx. The anything, right? Such dm, in any case, if it's like linear, it's just dm times the linear mass density times dx, dy or dz. If it's the area, the dm is it's not my linear mass density. It's probably like the area density, their area mass density times dA. This volume is my volumetric mass density times dV. And we also know that lambda is equal to gamma times x squared dx, so times dx. I replace this by gamma and x squared dx. We integrate from 0 to L. So it's equal to gamma as a constant, so we take it out of the integral. 0 to L x squared times x squared x to the 4th power dx, which means gamma divided by, we use power rule. It's the 5th power, so we divided by 5 from 0 to L is equal to gamma over 5 times L to the 5th. We know that gamma is 3m over L cubed, so I is equal to 3m over 5L cubed times L to the 5th. Okay? So which means L to the cube and L to the 5th are cancelled, becomes L to the square, L squared, so the answer is 3/5 and L squared, which is same as the answer for part A. It's this, the answer it gives to us. So part B, determine the horizontal location of center of, okay, we need to know where the center of mass is, and express the answer in terms of L. So we know center of mass is 1 over m times the integral of x dn. We integrate from 0 to L, right? And we also know that dm, we have done in part A, is gamma x squared dx, so just is equal to 1 over m x times gamma x squared dx. And we need to integrate from 0 to L, which is equal to gamma over m, integrate from 0 to L, x cubed dx. So gamma over m is x to the 4th power divided by 4 from 0 to L, which is equal to gamma over 4m times L to the 4th power. Gamma is 3m over L squared, L cubed, so 3m over 4m L cubed times L to the 4th power. L cubed and L 4th power cancel to be L and m cancel. So the center of mass is equal to 3 over 4 3/4 times L. All right. Part C, for an axis perpendicular to the page, is the value of the rotational inertia of the rod around point P greater than, less than, or equal to the value of rotational inertia of the rod around the rod's center of mass. That's obvious, right? That's obvious. The rotational inertia around the center of mass is always the least, right? Always the smallest. So it must be greater than the rotational inertia around the center of mass. So it's greater than, right? Because the mass is averagely further away from point B than the center of mass. Okay. Oh, part D. The rod is released from the rest in the position shown, and the rod begins to rotate the rod's horizontal axis perpendicular to the patient through point P. On the axis below, sketch the graph of magnitude of net torque tau on the rod and the speed omega of the rod as function of time t from this time the rod is released until the time its center of mass reaches its lowest point. All right. Okay. If we just look at this question, we think this question is really hard, right? So let's do some analysis first. The rod is initially the rod is horizontal on the horizontal line. When you release it, the rod becomes like this. Okay, the rod becomes like that, and it goes some angle theta. The rod center of mass is about like 3/4, so 3/4, so it's about here. This is the center of mass, and gravity is pointing downward, mg. Since this angle is theta, okay, what that mean? This angle is 90 degrees minus theta. What that mean? That also mean that this angle should be 90 degrees minus theta. And this angle, the component of the force that really contribute to the torque is the force perpendicular to the rod. And this part, because this is 90 minus theta, so it should be theta, which means the force is mg times, this is adjacent to the angles, is cosine theta. Okay? All right, so we know the torque is equal to mg. This is a force, so the torque is mg times 3/4 L times cosine theta. Actually, this coefficient 3/4 is not that important. So from that, we know that at first the force is really big, right? Because at first the angle is 0, so cosine 0 is 1, is the greatest, because cosine is the graph of cosine is like that, right? So at first it's really large, but it starts decreasing. So we definitely know that the torque at first is really large, but finally it's really small, which is 0 when it reaches the bottom. But what is the shape of the graph? We don't know the shape of the graph, right? But what can we do here is that we know that we can take the derivative with respect to time. So for the torque, so this is equal to 3/4 times mgl. Derivative of cosine theta is negative sine theta. And we're taking derivative with respect to theta, not with respect to time, right? But we need to know what's the derivative with respect to time. So we need to use the chain rule. The derivative of theta with respect to time is just omega. And we know the omega should increase, right? Because we have a torque here. So we have a torque, so there's always an angular acceleration, which means the omega must increase. So omega, and we also know that omega is positive. So when you take the second derivative respect to time. This is equal to 3/4 mgl are all constant. And we use the product rule. The derivative of negative sine theta is negative sine cosine, negative cosine theta. And derivative with respect to theta with the chain rule, which is omega. So it's negative cosine theta omega squared minus sine theta times the derivative with respect to the derivative of omega with respect to time, which is my angular acceleration. Is my angular acceleration positive? Yes, because we have a torque, right? We also know that the omega squared must be positive, right? It's increasing, so it must be positive. So this is positive. This is positive. How about like cosine theta and sine theta? Well, start from here to the bottom. At the bottom, theta should be 90 degrees. So if we are here, we are going from 0 degrees, so we know theta is from 0 degrees to 90 degrees. So it's in the first quadrant of the unit circle. So that means both cosine and sine are all positive, which means negative cosine and negative sine are negative. So this entire thing is negative. This is all positive, so the second derivative of torque with respect to time is negative. So the torque graph is concave down. So the shape should be like this. Something like this. Should not increase here. Right? Just it's always going down, but should be concave down here. Right? It's always going down. And how about the angular acceleration? We know that torque is equal to I times d omega over dt, right? And we also know that the derivative of the torque is equal to 3/4 mgl omega times negative sine theta, right? Same as we calculate here, and that should equal to 1/I times d squared omega over dt squared. So because these are constant and we don't need to care about them, right? And they're all positive, omega should be greater than 0. And we know negative sine theta is less than 0, which means this is less than 0, right? And actually, the second derivative with respect to time for the angular speed is less than 0. So we start from 0 and increasing. It's really concave down again. So it should see something like this. All right. So part B, as a rod rotates from horizontal position through the vertical, is the magnitude of angular acceleration on rod increasing, decreasing, or not changing? Justify your answer, please. Okay. From the graph, we have known that since the graph is concave down, well, it's more like decreasing, right? The angular acceleration decreasing. And we have known that torque is decreasing. And torque is equal to I times angular acceleration. Therefore, angular acceleration must be decreasing. Okay, that's for part E. Alright, finally we get last part, part F. The mass of rod is M is 3.0 kilograms and the length of the rod is 1.0 meters. L is 1.0 meters. Calculate the linear speed V of point S as the rod swings through the vertical position down with precision shown. So we have know that we need to use the law of conservation of energy. So at the bottom, Well, it is my height, right? So at first, the rod is like such. Remember my center of mass is 3/4 of the entire length, which is 3/4 times 1 meter, with 3/4 meter. This part is 3/4 meter. Basically, the center of mass goes down from here to here by 3/4 meters. So we know the change of the potential energy is m, which is 3.0 kilograms times 9.8 times my g times 9.8 and meters per second square times 3/4 meters. That is equal to 3 times 9.8 times 3/4 is equal to 22.05 joules. And that's my total energy, total potential energy. Okay, total change in potential energy. And that should be equal to my change in my kinetic energy, which should be 1/2 I omega squared. So, which means I omega squared should be 2 times 22.5, 44.10 joules. Omega squared is my 44.1 divided by I joules. So my omega is square root of 44.1 over I, which is equal to 44.1 joules divided 44.1 divided by my rotational inertia, which is I is equal to 3/5. Let's check it. 3/5 should be 3/5 and L squared, which is 3/5 times 3.0 kilograms times 1.0 meter squared. Okay, so which is equal to 3 times 3, which is equal to 1.8 kilogram meter squared. So it's 1.8 at the bottom. Should be in radian per second. That is equal to square root of my 44.1 divided by 1.8. Okay, about like 4.95 radian per second. So the speed at the bottom should be my omega times r, which is omega times L in this case. So V is equal to 4.95 times 1 meter, which is just 4.95 meters per second. Yeah, I think that's it. Thank you.